Right, thank you. So I'm going to talk about some recent work on nearly linear time algorithms for maximum flow and undirected graphs. Okay, so first, the maximum flow problem is just we're given a graph which has n vertices, m edges. The edges are capacitated, so for each edge there's some capacity, has the same capacity in each direction. And for each vertex there's some demand, bi, so bi can be positive or negative. If it's negative, we think of it as a supply. And so what we want is to find a flow, which is just an assignment from each edge to some real number. It can again be positive or negative, such that it respects the capacities, and that the net flow into I is bi. And I'm just going to write that by bf equals b. So b is just the matrix that maps flows to excesses. So this is a linear constraint. So I want to find a flow that respects the capacities, and such that the net flow into I is bi. Okay. So alternatively, this might not be possible, and the reason it might not be possible, well, so for example, if there were a set such that the total demand, the aggregate demand, so that on this left, this b, I'm using this notation bs to be the sum overall I and s of bi, so that the total aggregate demand into s, if that exceeds the total aggregate capacity that's into S, so I'm using a notation CS for that, well then clearly it's impossible to do what we want. There's no way that we're going to route, we can't flow BS into S if the capacity is less than that. So so given our input data, we want to either find the flow, or if it's impossible, we want to find such a cut. And so the well-known Max-Floman cut theorem says that these two cases are exhaustive. So either such a flow exists or a cut must exist. So in the case of an approximate algorithm, we're going to relax this further to say, well, instead of having the flow respect the capacities, we'll allow like a 1 plus epsilon multiplicative error. So alternatively, you can think of, so what is the justification for this? Well, you could also think of this as saying, well, if we were to scale down our demands by 1 over 1 plus epsilon, then we could meet them. So when you're going to consider an approximate problem, I guess there's a couple things we could do. So first we could say BF is not exactly equal to B, but that might be kind of useless. Probably if you want to route a flow, you probably want to route exactly the demand. So the natural thing to relax is to say, okay, fine, we can route the demand, but not as quickly, in the sense that we'd have to either scale down the demand or we would exceed capacities. So we're going to still require that we route exactly the demand. We're just going to allow a possible multiplicative error on the capacities. Okay, so this is a very well stated problem. This is a long line of history. So I'm just going to talk about the work that applies to basically the most recent work up until this. So for a while, the best known result was this result of Goldberg and Rao that actually worked in directed graphs and got a running time of m to the 3 halves. And then in 2010, there was this breakthrough by Cristiano, Kellner, Madri, Spielman, Tang that showed that, so now in the case of undirected graphs, you can get m to the 4/3. So this was sort of the first sign that, well, maybe undirected graphs are easier than the directed case. And then, so in this work, we get it down to basically nearly linear, so m to the 1 plus little f of epsilon. And independently, at nearly exactly the same time, Kellner, Lee, Arecki, and Sidford also obtained the same ultimate running time, but via a slightly different algorithm. So I'll just mention that basically both of these results were obtained using techniques that were introduced in the Spielman-Tang's paper for solving Laplacian systems. And I think it'd be accurate to say the philosophy for both papers is basically try to do for maximum flow what Spielman-Tang did for electrical flow. So you can view solving a Laplacian system as an algorithm for a certain kind of flow algorithm that does something different from max flow. It minimizes L2 norm instead of L infinity norm. And so the main difference between these two recent works is basically, so the KLOS algorithm is they introduce a technique to get 1 plus epsilon approximate flow algorithms from weaker approximate flow algorithms. And also in order to do that, they also had to present a new approximate flow algorithm. And also the approximate flow algorithm they presented is oblivious. So it also is of independent interest because it gives an oblivious routing scheme. The difference is in this work, it's a somewhat weaker requirement. We can get 1 plus epsilon approximate flow algorithms from approximate cut algorithms. So the result is that you get a simpler algorithm, but the two results kind of complement each other. So there's interesting things in both. Okay, so let me give an outline. So I'm going to talk about, so first, just the overall approach, what the algorithm is doing. It involves this notion of almost routing and recursion. And then I'm going to talk about the key ingredient that makes all this work, which is the notion of a cut approximator. And then I'm going to talk about the general framework in which this algorithm fits, which is basically demand infeasible Lagrangian relaxations. And then at the end, I'm going to give you the full algorithm. Okay, so the main result is, given the input, which are the capacities and the demands, basically m to the 1 plus the little o of 1 time, we can solve the approximate, so that by criteria. So we can either find a flow that routes the demands and such that the total flow on an edge is less than 1 plus epsilon times the capacity, or we find a cut whose aggregate demand exceeds the aggregate inbound capacity. Okay, so the plan for how we're going to prove this result and how the algorithm works is, so we're actually going to do we're going to look at a different approximation. So we're going to try to find a flow that exactly meets the capacity constraints and is sort of off on the demands. So we're going to find a flow that's exactly meets the capacity and sort of the demands are not quite met, but almost met. And once f is good enough, to say what that means, well, then we're just going to we'll just set new demands to be, well, whatever our error is, and we'll set new capacities to be something like epsilon times the old capacities, and we'll recurse. And if we can do this, then and everything works out, we'll get an algorithm that ultimately routes B. So we need to say why this works. What does it mean to be good enough? How do we know that the recursion will work, and so on. So that's what we're going to look at. And so when does the recursion eventually stop? So we'll see later that basically once you do this log m times, so the remaining error is so tiny that it's sort of trivial, right? So if you imagine you do this log m times, each time you're scaling down the capacities by a constant factor, you do this, say, log m times, your new capacities are like 1 over m of your old capacities. And it's pretty easy to get like an m approximation of maximum flow. Okay, so the most important ingredient in this is this notion of a cut approximator. So we have this following definition. So I'm going to say an alpha approximating cut family. So it's a collection of cuts such that for any demands B, I have this inequality. And so what does this mean? So basically what it means is if I want to know whether B is feasible in an approximate sense, this family will immediately answer it. Just if I'm only interested in the decision problem, I just want to know, yes, I can route it possibly with some expansion of the edge capacities, or no, I can't. So in particular, if I'm given some set of demands, if I were to just check the cuts in that set, well, certainly if I find a cut where the aggregate demand exceeds aggregate capacity, then I'm done. I know it's infeasible. But on the other hand, if according to just looking at those cuts in that family, it looks like it would be feasible, then the approximator condition, what it says is that in fact, the flow problem, if I were to scale up the capacities by alpha, that problem is feasible. So this is going to be the key ingredient to our algorithm. Okay, and so why is this useful? So I said before what we had to say is, okay, what do we mean by getting B minus BF small enough? Well, if I want to recurse, and I want that thing to work out, it means that whatever's left over, I better be able to route it in the graph using at most epsilon C capacity. If I want to ultimately use 1 plus it, since I already used 1, after I recurse, I can use at most epsilon. So we can observe from this condition that if I were to obtain this residual R, such that for all the cuts in this family, the error was small, in particular, let's say it was less than epsilon over alpha, well, then I know exactly what I want. I know that R, so that the new flow problem with demands R and capacities epsilon c is feasible. So this construction basically matches exactly sort of what we want in order to make this algorithm work.
Okay.
Okay. So the main theorem, the main subroutine that we use is the following. So let's let C be any collection of cuts, not necessarily the congestion approximate, the cut approximating family, but just any collection. So there's an algorithm we're going to call it almost route, such that given the input data and also given this collection, so it's an iterative algorithm. It's going to make some number of iterations. Let's see what they do. And so either, it finds the cut that we want, or it's going to find a flow that satisfies this relaxed smallness condition. So it's a flow it satisfies the capacities exactly, and the residual R equals B minus BF satisfies this relaxed condition so on any cut in the family, the congestion is less than delta. And so in order to get this less than delta, you basically need log size of C over delta squared iterations. Each iteration requires basically linear time plus checking all the cuts in C. So if you had a family of cuts that was, say, nearly linear in size, and it had some kind of structure that you could check all of the cuts quickly, you would get a nearly linear time algorithm. Okay. So now the important work comes. Okay, so we take this theorem, and now we're going to. So that theorem held for any family of cuts, and now let's just use that theorem with our approximating family. Okay. So let's say we have some approximating family, and let's say it's going to be linear size. Otherwise, it's useless. We're not going to get a linear time algorithm. So I'm going to replace the log size of C with log m. Okay, and let's take that delta to be, say, so remember we have, so the residual is going to respect capacities to within factor delta. So if we now set delta to be like epsilon over 3a, that 3 is just a little thing to help us out. We'll see why. So if you apply the previous theorem, we get after basically alpha squared over epsilon squared log m iterations. We're either going to get the cut that we want, or we're going to find a flow with that respects the capacities, and the residual satisfies, again, just from the theorem, the residual on the set S is less than I'm missing it should be a CS. Okay, so that should be epsilon over 3a times CS, both of those things. Okay, but so the point is, so we have that epsilon over 3 alpha, that's in the family, and then the whole point of the family is, well, once we have that condition in the family, now we can say for all cuts, RS is less than epsilon over 3 times the capacity, RS is less than epsilon over 3 times the capacity of S. So this means that whatever's left over, we know it can be routed with capacities epsilon over 3. So that means that now if we could just recurse, and once we recurse, we don't even need a really good approximation. If we could get it to within a factor of 3 when we recurse, then we have our epsilon. And we'll use some of that. So each time we recurse, so we need this little factor of 3 just because if we just had exactly epsilon, we'd have to solve it exactly. So we just give ourselves a little factor.
So at some point it seems like you have a cut oracle that tells you where small cuts are. How do you then get a flow? I don't understand how we go back and forth between. Just because I tell you there's a small cut doesn't mean you can.
So that's inside this algorithm. Yeah, so I'm going to get to that in next.
That's how you lost the hypothesis. So it's also a flow oracle?
Okay, so this is,
So it says somewhere under the hood is something that'll generate flows or generate.
yes, right. So that's what this. So the theorem in the theorem, right? So you take this theorem. So this is an algorithm that I'm going to state later in the talk. But what it does, so it says right here, one of the things, it either gives you a cut or it gives you a flow. So the flow is obtained by this algorithm.
We have access to an oracle for both flows and cuts.
No, this algorithm is going to.
The algorithm, but at a high level, there's some kind of black box that returns this stuff for you. Which
Yes, yes.
Is the theorem.
Yes, exactly.
And then from that, then we're trying to
So
improve it.
So once we have this, we're essentially done just by the recursion.
Wait, but I think he's asking what the hypothesis is. What does almost route need? And the point is, almost route only needs to be able to approximate the sizes of cuts. It doesn't ever. Almost route produces flows without ever being given any information about flows explicitly, right? I think that's what you're trying to.
Exactly. So almost route does all the flows. What it needs is just this set of cuts C. That's all it needs.
So you're explaining how to go from some kind of cut oracle to a flow.
Exactly. Right.
But it's not a general cut oracle, right? It's like this family.
It's this family, right?
But yeah, or some other kind of thing.
Right. So exactly. So almost route is the algorithm that, given this cut oracle, is going to implement this approximate flow oracle.
Okay. Just to refresh my memory, you said once we have this, or the thing 2 slides later, we're done by recursion. What exactly does the recursion look like? I missed. You probably said that earlier, but it was that you.
Okay. So we know.
You this flow, then you get the residuals.
Yeah.
And then,
Okay. So we said that. So right. So this corollary was that whatever's left over can be routed. We know that if we were to take the capacities and scale them down to epsilon over 3, we could route it.
okay.
Okay, so that means, say, if we were to even just find a 2 approximation for that flow, we would still have it with, then we would get 2/3 epsilon. So so once we've recursed once, we never care about epsilon again. We can just keep getting constant factor approximation. So that little extra factor 1/3. So this sum is gonna be a geometrically increasing sum. It's gonna be bounded by epsilon.
Okay, so when I think about the recursion, I think the top level is different from the levels that are coming.
Yeah, exactly. So, the top level is different in that that's really the only one where you care about this epsilon. After the top level, the factor to which you approximate can be a constant. And also, once you, after the top level, you'll never find a cut because if you're going to find a cut, you'll find it at the top level because once you recurse, you have this property that the problem that you're recursing on is flow feasible by this property.
I mean, the usual trick for flow problems is you get residuals, but that's directed graphs. So somehow, so somewhere in here is a subtle point about not ending up stuck with directed graphs.
Right. So the residual is residual demand. So what I'm saying is you basically just start. So this is a very pessimistic estimate. I'm saying I have some flow that I know all the flow on each edge is less than the capacity. It could be much less. It could be exactly. But then I know that whatever's left over can be routed with at most epsilon times the capacity. So certainly if I were to just take the sum of the flow I have and that other flow that I know exists, that would certainly congest any edge by at most 1 plus epsilon. So we're not taking any residual graph. When we recurse and we get a new flow problem, we're using the same undirected graph just with the capacities scaled down by epsilon.
So somehow it's good enough so that you can just work with absolute values of the capacities rather than working with the residuals.
Right.
Approximation. Somewhere under the hood, that's what's happening, right? Okay.
So if your flow is equal, the demand is actually equal to the smallest cut, then in fact after the first step you can stop, right? Because you have a 1 minus epsilon flow at that point.
Wait, sorry, what was that again?
So if your demand is tight in the sense that it's actually equal to some cut, the minimum cut, then,
So
then you can stop.
once you find a cut, you stop immediately.
No. Even if you find a flow, I'm saying if the flow is tight, if your demand is actually equal to the minimum cut.
So what do you mean demand is equal to minimum cut?
So if your whatever the demand B is.
So you mean if B equals BF?
If B equals minimum over all cuts CS.
I'll follow.
B is a vector,
He's saying
right?
if you compute a flow and that flow is tight in your first iteration,
Meaning it satisfies the
there's a
demand exactly, but that's never going to happen.
there's a cut. That's
Yeah.
but
Okay. Maybe you can go off.
What's the size of a? How do you decide the size of an approximating family? Is it the
The number of sets in the family.
number of sets? Okay.
But you're also assuming something like you can compute the size of all these cuts efficiently, right?
Yes. Right. That's what I said in the.
Yeah.
So each iteration requires linear time plus checking all the cuts.
Okay.
So I just want to give some examples. So these cut approximators, they seem extremely powerful. In fact, the first time you see the definition, it's like, how can this even exist? So I want to just give a few examples, so at least before I get to the algorithm, you'll be convinced these things, they really exist. Okay, so I want to look at the simplest. Here's the simplest cut approximator, and if you use this, so if you had a graph that had large conductance, this would be the algorithm that you would want to use. It would be extremely simple. So we'll get to it at the. Okay, so let's say we have a graph that has large conductance. So what that means is that for every cut S, the total capacity of edges crossing that cut is at least phi times the minimum, so over the smaller of the two sets, of basically the total number of edges just that are incident with that set. So if I define, say, the volume of a set as just the total capacity of all edges not leaving that set, but just the total capacity of edges incident with that set, then a graph has conductance phi. So basically what it means is the capacity of any cut is at least phi times the total capacity of edges incident with the smaller side. Okay, so in a graph with this property, then I'm going to claim that the family just of singleton cuts, so just the cuts where you just look at cut off a single vertex, there's n of them, those single vertex cuts, that's a phi inverse approximator. Why? Well, okay, so let's suppose that we have some cut S where the aggregate capacity the aggregate demand exceeds the aggregate capacity. And without loss of generality, we can assume that V of S is the smaller side because, note that, so since the total demand has to sum to 0, I forgot to mention that at the beginning, but this is clearly you're only going to find a flow if your net the sum over all vertices of the demands should equal 0, because flow is conservative. You can't just get stuff from nowhere. So that means that in particular, the aggregate demand into S is minus the aggregate demand into V minus S. So the absolute value of the aggregate demand on both sides of any cut are the same. So, right, so if I had this condition, so I'm going to just assume that S is the smaller side, because otherwise I would just swap S and V minus S. Okay, well then, so I know then that, well, if I were just to look at the sum of the absolute values of the demands, that's certainly bigger than the absolute value of the sum of the demands, which so this is bigger than CS by assumption, which is bigger than phi VS, which is phi sum over CI. So so remember I use that notation C sub S to be the capacity of edges leaving the cut. So C of singleton I is just basically the total capacity of edges incident with I, or the weighted degree of I. Right? So then if this holds, then, well, some I must have BI bigger than VCI. So in a graph with large conductance, all you need to do is check the singleton cuts, and that gives you a phi inverse approximator. In other words, take any set of demands that if you were to just look at the singleton cuts, so the aggregate demand into any vertex is no more than the total capacity of edges into that vertex. If that's true in a graph with conductance phi, then the flow problem where you scale up all the capacities by phi inverse must be feasible. That's what this is saying.
So just make sure I understand. So, and if you were running your algorithm on this graph, then you would need that, or would you have to recurse then on graphs that were no longer high conductance?
When you recurse on the same graph. Okay. So, right. So because remember, so when we recurse, we scale all the edges uniformly.
Okay.
So it's equivalent to just scaling the demands, right?
Yeah. Yes. Yeah. Okay. So I'm just going to state some other ones. So I gave this one. So I'm not going to prove these, but so another example, if you let T be a maximum capacity spanning tree, so that's maximum, let's say like a maximum weight spanning tree with respect to the capacities. You just look at now the single edge cuts, where you cut a single edge out of that tree, that gives you a factor M approximator. And intuitively, the reason is because, well, if you look at any cut in the original graph, it's bigger than, and you look at the capacity of that cut in the tree, it's bigger by at most a factor of M. So for a 2D grid, if you were to look at this family of cuts, so look at the single vertex cuts, but then I also look at, say, 2x2 subgrids, and I'll look at, say, 4x4 subgrids. So basically look at all the power of 2 subgrids. This gives you like a hierarchical decomposition. This gives you a log to the O of 1 approximator.
1, 1, actually?
I don't know. That's why I put O of 1. I think it's 1, but exercise. All right. Okay. So another real due to bracket is, so for any graph, there's a similar kind of hierarchical decomposition that gives a log n approximator, and it can be found in polynomial time. So then, but if you want a linear time algorithm, that's not quite good enough. So the thing we actually need to use in our algorithm is this result of Madri that says for any graph, there's a set of n to the 1 plus little o of 1 cuts that yields an n to the little o of 1 approximator, and it can be found in nearly linear time. And so the main result, so we actually get our algorithm by using Madri's approximator, and then we just need to do some minor data structures work to show that we can check all of the cuts quickly. Notice that in the case where you have one of these hierarchical decompositions, it's very easy to see that you can check the capacity of all the cuts quickly. Just by doing it, it's basically a tree fix sum.
The Rocky O1 is not hierarchical, right? So it can...
The Rocky one is hierarchical.
Oh, the...
Madri's is not hierarchical.
Oh, it's polylog. It's a polylog one. It's not the log n.
So Rega has several. The first one is hierarchical.
And it's log?
Right, it's a polylog, it's not a log.
So the one that you get an exponential time is log, is that?
The Ricky 08 one with a bunch of trees.
Okay, that's right. The one in this work is not log. Yeah.
And then that's checkable or not?
Yeah. That one's checkable, but the total size is fairly big. So it's unclear.
Okay. So now, okay, good. So I told you about basically the basic idea that we were going to do, the almost routing and the recursion, and I told you about Cut-Approximators. So now I'm just going to say, okay, what are these demand and feasible Lagrangian relaxations? And we'll get to the algorithm. And okay, so let's talk more about this matrix B. So let's remember that if we had a flow, then BF sub I is the net excess into I. So we can think of B as basically like a discrete divergence operator. Actually, negative B is the discrete divergence operator. Okay. On the other hand, what is B transpose? So if I have some function Pi defined on the vertices, B transpose P on an edge is basically the difference between the difference over that edge. So it's like a discrete derivative operator. So particularly, I want to consider the case where I want to say Pi is a collection of prices, and I want to imagine that vertex I announces that he's willing to buy or sell an item, whatever it is that we're transporting in this network, for Pi. So I'm going to give an economic interpretation of what these algorithms are doing. So suppose that in response to the vertices announcing these prices, the network were to decide to buy some FE units from I, transport it to J, and then sell to J. So the total profit would just be the sum over all edges of the amount that's transported times the price difference. So the point is that's when if you see some form like this, P transpose BF, what that quantity is the total profit for transporting according to F with prices P. So if such prices P were declared, the best thing you could possibly do would just be for each edge to say, look at the two endpoints, buy from which full capacity from whichever one is cheaper, transport that full capacity across, and then sell to the larger one. And that would earn a total profit of sum over all edges of the capacity times the absolute value of the difference. On the other hand, if the network had actually routed B instead, the total profit would be just this sum over all I pi bi. So we can observe that if for some prices it were the case that, well, the total profit that could be achieved by routing B was larger than the largest profit that the network was able to obtain, then, well, this must tell us that that B must be infeasible. And indeed, that's the case. You can show, again, it's a fairly simple exercise, that one of the, well, so first, this immediately, just by definition, P is basically a hyperplane separating the set of flows Bf equals B from the set of flows that respect capacities. But you can also get a cut from this just by, if you look at some sets of the form, the set of all vertices whose price is at least T for some T, one of those, or the threshold cuts, one of those cuts is going to have the condition we're looking for. So the way the way our algorithm is going to work is, so these Lagrange relaxation, that was basically, in some sense you can think of it as simulating the dynamics of a market that would solve the problem. So on each day, the vertices are going to announce their exchange prices. Each edge is going to respond greedily just by doing exactly what I said before. It's going to take full capacity, buy from the cheaper, sell to the higher, and earn that much profit. Then the vertices in response are going to use those flow results, or I guess actually just they don't need to know the actual flow, they just need to know how much they bought and sold. They're going to use those to update the prices for tomorrow, and they're going to do what you would expect. So in particular, if there's vertices where the demand was not quite met, they're going to raise the prices there. And if there's vertices that were oversupplied, they're going to lower the prices there. And in fact, we'll see the algorithm, if I take that singleton cut as my approximator family, it literally, the prices are just going to be completely local, just dependent on whether demand was met or not met just at that vertex. And so the idea behind this is, well, so hopefully if we sort of dynamically adjust our prices in a reasonable way, we should be able to show something like the average flow. So if we take sum overall, so if we look at just sum over all days, so this is a flow that it's like T times too big, so if we just take it and we average it by T, this should converge towards B. Or alternatively, some days prices will prove infeasibility. So this is the basic flavor of, so this is an entire, so this is this is basically a framework, a huge family of algorithms. So you have to specify the method for updating the prices. And so for any method of updating prices, you get an algorithm. Okay. So on day T, let's let R be the residual of the total flow seen so far. So basically what the algorithm is going to try to do is going to try to minimize some function phi of R. It's going to try to keep this function small. And the prices are basically going to be just the gradient of phi of R. So it's basically the way it's going to price a vertex. The vertex is going to price its commodity according to the marginal cost with respect to this function psi of additional units entering or exiting the vertices. And the choice, so that therefore the choice of this function psi determines the price updates, and that determines the entire algorithm. So if I once I state so if I just pick a function psi, then the algorithm that I said before, so you use the gradient as the prices, and you run the algorithm I said before, and that's a complete algorithm. Okay, so we just need to say, well, how do we pick psi? Okay, well, so remember what we were trying to do. So what we wanted is we wanted to minimize this. So So psi of r should be a smooth approximation of the maximum overall sets. Sorry, that should be RS over CS. Right. So that's what I really want to minimize. Right. My goal is to ultimately find a residual such that the maximum overall sets of the residual divided by the capacity is small. So there's various things you could use. You could use different functions. I'll just pick. So in particular, so this is like an infinity norm. So in particular, if you take a Q norm for Q like log n, where the Q norm sort of crudely approximates the infinity norm, and it's differentiable. So the final algorithm then is just going to be exactly so it's going to be the algorithm that I said before, using this as the psi function. So and then we can basically interpret what's actually going on is, so if we look at, so where do these derivatives come from? So on a given day, we can basically say each cut, so it looks according to what is the residual, so far, what is the residual error across that cut? And based on that residual error, it's going to declare a price per unit crossing that cut. And then from those prices per cut, we're going to say, okay, so to transport, the cost of transporting from I to J is just the sum overall cuts that you cross of the price for that cut.
So at a high level, so what we do in the middle of trying to figure out how to find a flow?
So this is the flow, right? So where do the flow cut?
Flow algorithm.
Right. So this is where the flow algorithm. So the flow is going to be this average flow. So this is where, right, so this was where the flow came from. So we iterate, right, so it's on each day we pick this, we just greedily pick this flow, and in fact it's sort of really stupid. It's going to send full capacity in one direction or the other, even if.
Where in the algorithm do we use the demands?
Right, so the demands were here. So R is the difference between the total flow I've routed so far and how much, and this is what should have been routed so far if they actually respected the demands.
What's T?
T is on day T. Right, so it's been T days, so if the network routed what we wanted, the net flow would route T times B, right? On each day they would route B. So R is the difference from what we wanted, difference between what we wanted versus what they actually routed.
T is a scalar?
Sorry, T is day T.
There's a scalar for day T.
Yeah, so day 1 up to...
Number of iterations. You're on the Tth
Okay,
iteration.
iteration.
An integer.
Yeah.
Capital T is an integer.
Yeah.
Okay, good. All right, good. So, yeah.
So, and that's...
So this version has a constant step size, is that correct? You're always...
Yeah.
Wait, can you scroll back to where you just put in that function phi? Wait, it's up just a little, I think. Oh no, wait. Somewhere you had this p tilde s, the price tilde.
Oh yeah, I mean, there's later.
Oh,
So first we had the generic framework, and now we get the specific algorithm. We specify this function, and that gives us a concrete algorithm.
It's quite the same algorithm in your paper, right?
It's not quite the same, but it's
You've changed
essentially the
the
same.
method a little bit or something?
Oh, sorry?
You've changed the iterative method a little bit?
Slightly, yeah.
Okay.
But
Is there any sort of, does this actually have any implications or can
no, it's just simpler. It's just simpler.
Okay.
So you said the prices were going to be the gradients of the potential function. Is that clear that that's what's...
Yeah, exactly. Right. So
this pi would be the gradient.
that should be no. Sorry. That should be RS over CS to the Q minus 1.
Okay.
It's definitely in the tab.
RS over CS. That's RS over CS to the Q minus 1.
Yes. Okay. Then it's...
And then it's the gradient. Yeah. Right. So in particular, right. So what's going on? It's basically giving.
Maybe times.
It's putting basically all the prices are going to come from the most congested cuts, right? This by raising that to this Q minus 1, this is a huge power. Basically, the only things that are going to contribute are those cuts that are with it to the only thing that are going to contribute to prices are those cuts that are like nearly maximally congested.
One other thing, so when you say you're using power Q proportional to log of the cut family, are there also some hidden epsilons in there, like log cut family over epsilon or epsilon squared or something?
No, the number of iterations determines.
Oh. Okay.
So this power to the Q is similar to the softmax.
Yeah, exactly. So in the paper I use the softmax. Softmax is like log is this function that you commonly see in multiplicative weights, log of sum of e to the x. Right. This is like an approximation to max.
And this is also an approximation to max. The thing you wrote down.
Yeah. But if you use this, then you have, because we care about the sign, right? So we care for RS over CS is very large, very positive, or very negative. So this is for things that are positive. So you have to, if you want to use softmax, you have to make it something like log of sum of e to the xi plus e to the minus xi, and do something like that. If you use these, you don't have to worry about that.
And here for each cut, you mean each cut in the...
each cut in the family.
Approximator, right?
Yeah, right. So for each...
Yeah.
Yeah, so the function is the sum over all cuts in the family of just this function, this basically this Q norm of that. So in particular, let's say we had a graph that had large conductance. Then, right, these sets are just the singleton cuts, and then literally all the algorithm is it's keeping track of, there's some residual at that vertex, and it's basically just, so the naive thing to do would be to just say, on a given iteration, I'm just going to say, okay, whichever vertex, if this vertex A has more residual than vertex B, I'm going to move from A to B. That's a little naive. What you really want to sort of normalize by the capacities, and so, right, so what this is doing, so instead of just moving by whichever one's residual is larger, it's moving by whichever one's residual to the Q minus 1 over C to the Q is larger.
Was an algorithm like that known before for flowing expanders? I mean, it's a very sort of elegant sort of algorithm.
Not that I know of.
Just sort of flooding and...
Yeah, no, not that I know of. I mean, that's right. I think if that were sort of once you have that and you have the ideas in Spielman-Tang, you sort of have the rest of it, right? This is sort of because sort of this algorithm is sort of
push relabel flavor.
Yeah.
This is I guess I would sort of think of this as like just doing gradient descent in a to solve a Laplacian system using or maybe using a diagonal preconditioner just to say a diagonal preconditioner by the.
So with the Kellner et al. Paper involves like constructing oblivious routings on expanders by using electrical flows or something. So would that also do the same? Would that also just, if you had an expander to begin with, I assume that would also give you a fast algorithm for expanders comparable to this, or?
No. So their algorithm is going to take the same amount of time no matter what. Right. So.
You said you have this better cut family for expanders, right, where you just use the single vertices.
Yeah.
And their algorithm is using these oblivious routings instead of the cut families, right? But they're producing the oblivious routings through schemes that involve recursive partitioning, and eventually they route expanders specifically just using an electrical flow on the expander, I think.
Right, but I see what you're saying. So if the graph was an expander, it would. Yeah.
I'm not sure exactly how much.
I'm not sure if it'll be. It could be similar. It's not. It's definitely not going to be exactly the same.
Right.
I don't know, a few iterations of electric flow versus flooding the degrees. I don't know which is faster. If you do it right.
So I think if you told me write a Maxwell algorithm in 5 minutes, I would probably write the one for the expander. Because it's literally just moving. There's not quite by moving from more residual to less, but if you suitably adjust by the capacities, it's essentially just that kind of flooding algorithm.
I mean, it's usually just applying multiplicative weights to the expander.
Right.
Works is what you're saying.
Yes. Yeah. So
Right. I mean, that's what this looping needs to with these paths. Kind of. Like there's a path, they did multi-quantity flow with these kinds of algorithms, and you can do it because the paths are short. You can either do it that way, just throw in the path.
Okay, yeah, I guess
But you can also do it because the problem is the conservation. And the conservation, you get screwed in a regular graph because the paths are too long and you multiply them together too much. But here, you don't get long paths, so you only pay a log n. Quadratic and log n.
there's no paths in this, so I don't know how to compare it to.
Well, I'm saying the same thing as what you're saying. Okay, so what you're saying is that if you just apply somehow, if you just apply multiplicative weights to all the constraints, which is that
Every cut?
no, all the constraints are the single edge cuts. You can do that in any graph.
What do you mean single edge cuts?
I mean the single vertex cuts.
Yeah, single vertex cuts.
Okay, yes.
The whole problem is the conservation constraints. I mean, in the whole flow, the problem with it for multiplicative weights has always been the conservation constraints. But here you're saying, okay, well, it's not such a big problem in the expanders because of this analysis, right? But you don't have a path argument. Somehow you're going through this whole congestion approximator to make it say, oh yeah, of course.
Right. Yeah. So the reason it works in the expander is because, well, in the expander, being if your residual is small on every vertex, that means you're good to go on the recursion. Because if your residual and the graph is an expander and the residual is small on every vertex with respect to the capacities, well, then you can just recur. You know that you can recurse because by the thing I proved earlier.
Yeah, that's very much not true in other graphs.
Right.
Those residuals are, if you don't obey the conservation constraints exactly.
Right. Probably a nice example is if you consider what would happen if you tried to use like the naive expander algorithm on, say, like a path. Right. So yeah, the conclusion. So the expander algorithm says, oh great, after like 1 over epsilon squared iterations, the residual flows. Okay, so sorry, let's say it's a path, and I have, say, 1 demand here, -1 here, and 0 everywhere in the middle. So the conclusion of the theorem is that, so after 1 over epsilon squared iterations, the residual on every vertex is less than epsilon. Okay, so that's easy. If all I need to do is move this, push this 1, sort of smooth it out over the first 1 over epsilon of these, and take this -1 and smooth it out over the first 1 over epsilon of these, and then I'll have that conclusion. But in the case of a path, that conclusion is completely useless because just having residual epsilon on all of the, if I had epsilon, epsilon, epsilon for a bunch of these and minus epsilon, that still doesn't mean I can actually route it. In fact, I can't.
So the difference is here, what your algorithm is doing is actually taking a look at every single cut along the way.
Yeah. So a path is kind of easy because it's a tree. So I guess So I said an example in the case of in a graph, if you look at a maximal spanning tree and you look at the single edge cuts, that gives the approximating family. So, and that would be exact. So the more natural thing is the grid. So the grid has the same kind of problem. If I say I put a bunch of sources up here and a bunch of sinks down here, if I try to use just the local algorithm, it's going to take root n time for iteration. So basically, for the first root n algorithms, these guys in the middle are going to do absolutely nothing because they see no information. Whereas on the other hand, if I add now these power of 2 cuts, and I use that as the approximating family, then something right on the boundary, an edge. Okay, so let's say there's a bunch of sources over here. There's a bunch of sinks over here. So naively, if I just looked locally, these things in the middle would never do anything. But if I use this power of 2 cuts, in particular, I look at these cuts, then these edges are going to see, oh, look, even though there's no local demand, there's a large aggregate demand into this cut. And therefore, the price for this cut is going to be large. And therefore, that's going to contribute towards even a vertex that's right here. It's going to contribute towards price. And therefore, even from the very first step, these edges are going to start pushing across.
Cool. That's great.
Yes, that's exactly what
Nope.
it is. Wait, so actually this way. So for this picture of looking at these things in terms of prices, so basically is what you're saying that if a cut, like if you have a lot of demand to route over the cut, basically we'll effectively try to do something like send stuff over that cut now rather than waiting till the flow gets there, or like that's how it's non-local in some sense.
Yeah, I don't know what does it mean for waiting for the flow to get there, but
I think that makes this different from like the local algorithm over the, that would screw up on the path. I guess is that you're saying that it will basically start putting flow on those edges immediately because it sees that those edges are like across cuts that are.
Right. Because there's a large aggregate, so one of the sets is in particular this huge set, and that set is going to have a large price. And remember, I said so the price on a local vertex is the sum over all sets containing it of those set prices. So that's why so the information propagates faster.
And these prices are some kind of gradient of.
Yeah. So the local vertex prices are just exactly, they're always just the gradient of psi with respect to r, right? So if I now put psi as this particular, like this q norm, then, right, so if you first just look at the function just with respect to each s, you get, okay, that should, if you have the q minus 1 there, right, that's, if you look at it as a function of residuals across cuts, you get that derivative just rs over cs to the q minus 1, and then when you transfer that to the individual vertices, you get that extra 1 over cs factor, and so then the derivative, the partial derivative at vertex I is just the sum over all sets of the contribution of like that derivative with respect to s. And it basically comes out to.
Anyway, in this particular iterative method, there's nothing that actually really looks like a gradient of the cost of your actual current flow. Is that correct?
Yes. Okay. You're right. So so there's a different. Yeah. So there's a difference. Yeah. So there's a different. Right. So that's one slight difference. So in the paper, there's. That's why I didn't give it the same title as the paper. It's not quite exactly. So in the paper, I also have this like weird, sort of strange function that accounts for both the error in the residual and the congestion. And so this is a little simpler. In fact, you don't need to have any function for the congestion. You can just always enforce capacity feasibility.
So is there one more stupid thing? Is there any kind of scheme? Like, does this come out as a natural? Like, the one in your paper was some sort of version of gradient descent. Can you get this as this iterative scheme as some kind of descent scheme?
Yeah, right. So that's the interpret. Right. So that's exactly what the psi is. So it's so you're not quite descending. So I guess in this interpretation, it's not really descending. It's sort of trying not to increase too much. But I mean, this is just from the fact that this r is growing. Because we're adding, right? So this r it's not the average. It's not the average residual. It's the sum over all days. So it's going to grow. We just don't want it to grow too fast.
Sounds almost like multiplicative weights.
It's exactly what it is. Yeah. So there's a sense in which you can think of. So multiplicative weights does exactly the same thing. Yeah.
Oh, Richard.
Sorry, I probably missed this, but is there a clear rule of, like, is there a specific point where you say how you pick the flow from the vertex prices?
Yeah. So that's just, it's always the greedy flow.
So you always put C capacity units of flow in either direction.
Yeah.
It works. I mean, it's not the smartest thing, but it works.
Are you considering releasing another version of your paper?
Yes. Well, my thesis, and I'm writing a journal version.
Awesome.
That has this I've been thinking a lot about it to try to simplify it. So.
Okay.
So is there any way of saying simply what properties you need of this function psi? Because you didn't really give us the analysis in terms.
Yeah. No. Well, the analysis is frankly not very interesting. It's if it's just the same as multiplicative weights, it's just Taylor expansion. Okay. It's just, I mean, so the point is to bound. So okay, so the point is, right, since I said the prices are the negative gradient, yeah. By the flow always choosing, like doing this greedy making this greedy flow, it's basically taking the largest step against the gradient, subject to respecting the capacities.
Okay.
So you probably just want the gradients not be too big, or
so what you need is basically the exact condition is that the second derivative, so the gradient should not change too much on each step. And what that means is basically the second derivative should be bounded in the L1 norm, or the dual norm to sort of the capacity norm.
But, I mean, can you just do straight multiplicative
Yeah,
weights?
you can use multiplicative weights as a black box. That's why I didn't do the
But it's not even a gradient thing, it's just multiplicative weights.
multiplicative weights is gradient descent.
Yeah, okay, but
So if you want, I mean,
but it's like a two-line
I
calculation.
think that's what I did at Fox. But if you want to present it in multiplicative weights, you need to like define a game where these, instead of these things being prices, they're probabilities, and it's like you have to.
If you just go down to the slide, you can almost see it almost trivially. It's to go to
Slide.
the residual there. You see the residual on day t, that's the residual, t times b minus b minus the sum. He shows every day the residual is that sum is less than 0 or something. It's less than some value. On average.
No, so the actual, if you want, the actual statement is basically, so we know. Okay, so basically this condition on. So for how am I doing for?
we're over time. That's okay.
Okay, well then I'll just do this last thing. Okay, so basically, if you want to look at the analysis, basically, so remember we said that if we had B dot P bigger than some overall E of CE PI minus PJ, we stopped. Okay, so basically, if this condition doesn't occur, that means that, so the minus gradient psi dot B minus BF is less than 0. So the first order change in psi is that it's shrinking. Or I mean, if this were to be exact, or that it's staying the same. So basically, so what that means is that psi is only going to grow second order. So in particular, if you take, yeah, so the growth of psi only gets contributions from the second order term. That's what ultimately allows you. So you ultimately you can prove something like psi. Okay, so if psi of r, if I were to say this is rs over cs q norm. Then you get something like if r is less than or equal to square root. So this on day t, this is less than or equal to square root log n times t. And the point is that, right? So clearly, if it was infeasible, psi of r would have to grow like t. So if you get this sublinear growth, then when you take the average flow, the residual is going to get smaller. And so you get this because the first order contribution to the growth is 0 or less than 0. That's what basically gives you the sublinear growth. It's exactly the same as multiplicative weights. I didn't do the analysis because it's not interesting. It's just Taylor's theorem. Any other questions?
Okay, thank you very much.